we were looking at the mechanics of balancing, and we looked at the case where the person starts to topple and you try to arrest it by moving the other segments, by transferring the angular momentum to the other segments of the body. If you look at it from a force or a moment perspective, essentially what you are doing is you are applying a moment. Your muscles are your actuators. So, right, you are applying a moment to rotate your to accelerate your arms. Okay. So, to change the angular velocity of your arms. So, when you do that, there is now a reaction moment applied to the rest of the body, right. So, if I apply a clockwise moment to my arms in the same direction that I am toppling, the reaction moment is now actually counterclockwise on the rest of the body. So, that is how I am trying to adjust this, change the tipping, trip it back to the erect position. So, if the reaction moment is sufficient to overcome the tipping moment, then I am able to regain my balance. Similarly, even with the case of this. So, if I have, so that is the reason you rotate your arms in the same direction as the toppling, because the reaction is what you are using to straighten the rest of the body. Okay. So, here for instance, if this is the direction of toppling on the tightrope, then if I create a moment at my shoulder that will rotate the arms clockwise, then the reaction. So, if this is like this, then on this body the reaction moment is like that, okay, which will tend to straighten it out. If I have the pole which has a large moment of inertia, basically I am applying. So, when I rotate the pole in the same direction, I am basically applying a force like this, right. I am applying a force on the pole like this. Okay. The reaction force creates a moment that will try to straighten this. Okay. So, that is it, that is the analysis from the force or moment perspective, because your force, the actuators in your body are only the muscles, and they act on these various segments in this manner to try to restore the balance. So, before we go to human walking, there are some more. So, this is essentially what happens with a lot of our movements. We were now looking at this case where we started off with two masses, right, on a frictionless surface, mass 1 and mass 2, and I have some kind of an actuator that can apply a force to these masses. Okay. So, if this is my y axis and this is my x axis, and say this is my frictionless surface, we saw that if I look at M1, okay, I am just looking at the horizontal motion. So, I have a force F1 applied to M1, and in this case say I have a force F2 applied to M2, and here F1 equal to F2 equal to F. Okay. I have an actuator that is applying. So, now I have, in this case, if I minus F1 equal to M1A equal to 0, these are equal and opposite forces. F1 equal to minus F2, therefore, F1 plus F2 equal to 0, and I can write that as M1 delta V1 plus M2 delta V2 by delta T. So, suppose I take this as R1 locating this mass, this as R2 locating that mass, this is equal to 0, and therefore, m1 delta r1 plus m2 delta r2 equal to 0. Now, what is my center of mass of this system? If I take RCOM, that is equal to m1 r1 plus m2 r2 by m1 plus m2. Okay. If I have the center of mass of this somewhere. So, if I look at the delta of the RCOM, it is nothing but m1 delta r1 plus m2, since I am all taking everything in the x direction, I will just not use this, m2 delta r2 by m1 plus m2. So, what this tells me is that this is equal to 0. There is no change of the center of mass. Okay. So, if I have two internal forces, okay, the internal forces, if one moves away, if one moves in one direction, the other is going to move in another direction in such a way that the net center of mass of the system remains the same. Okay. There is going to be no change in the center of mass. Now, let us look at the case. If I just move one segment with respect to another and there is nothing, I am isolated, there is nothing else happening, you know, I apply muscle forces to move one, I can't change the center of mass of the system. So, then how do we move from place to place? How do I? Because movement is basically moving the center of mass from one place to another. So, now let us look at the effect of having some kind of a support. Okay. So, let us say in this case now, the masses, at least one of them is against a support. Okay. Again I do the same thing, I apply set of internal forces which are equal and opposite, and now this is a support. So, it applies a reaction. Okay. So, if I look at the free body diagram of M1, I have this force F1 acting on it, I also have an R, a reaction force from the support. Then if I look at M2, M2 only has F2 acting on it. Okay. So,
F is an actuating force, internal actuating force.
F is the internal actuating force. F is an internal force, actuating force. So, I have here F2 equal to F, okay, F1 equal to R minus F2 in this case. So, now if I do the same thing, M1 delta V1 by delta T plus M2 delta V2 by delta T, now it is non-zero. When I have a support, okay, this is non-zero. So, now the reaction force is going to help me move the center of mass of the system. So, in a sense the reaction force is what becomes the propelling force. Reaction force only arises because of the internal forces. The internal forces acting on the mass which is against a support is what produces the reaction. If there was no support, then the net center of mass of the system does not change. Center of mass of the system does not change. But if there is a support, now the center of mass of the system can change. See F1, this is okay. The force on this is R minus F1, F2 is R. Did I mess that up? See F2 equals F, okay. This force equals minus F, right, this. So, let me just write it as, so I have F, I have F, magnitude is this. So, if I write it in vectorial form, R, say this is F1, let me just call this F1 plus F1 equal to M1 delta T F2 by delta T, but F1 equal to minus F2, right. So, now am I F1 is equal to the force R minus F is this. So, R minus M2 delta V by delta T equal to M1 delta V by delta T. I don't know what. Okay. So, this is how you get this. So, this is kind of what happens in your body. So, when you look at, if you take your upper body and say you take your lower body, let us just take it as a segmented thing. Okay. Suppose you create a muscle, using your internal muscle forces, you create upward acceleration, you make your upper part of the body, you give it an upward acceleration. Okay. That creates a reaction force on the lower part of the body, which is transmitted to the ground. Now, that is what causes your reaction force. So, the reaction forces are caused by your muscle forces. Of course, gravity is also there, apart from gravity. I am saying additional reaction forces come into play because of your ability to exert muscle forces, and that is what we use to move our so, it is the GRF is typically therefore a good indicator of the muscular effort that you are applying. Okay. So, you could be so for instance, when you jump, everything is happening because of muscular effort. You are applying the muscular effort to propel yourself, to give you a GRF that is enough to lift your center of mass. So, if you are airborne, okay, when you are airborne, you do not have any support, assuming negligible air resistance, there is no support acting on the body. In that case, you can move your limbs any which way you want, but the motion of the center of mass of the body will be influenced only by gravity. So, if you look at a lot of airborne movements, if you are looking at the linear motion, you only treat the center of, you take the center of mass, you treat it as a particle and you look at the motion of the center. Someone is doing a somersault or a jump or something like that, you can treat it, if it is only under the influence of gravity, then you treat it as a point mass, because there is no amount of internal manipulation that you can do when you are airborne to change the center of mass, because if one part moves up, the other part moves the opposite way, so that the system center of mass remains the same. Okay. On the other hand, if you are airborne, you have a net external force which is gravity, but the gravity acts through the center of mass. So, there is no external torque on the body. So, when you are airborne, angular momentum is conserved in that case. Okay? The angular momentum of the system remains constant once you are airborne. So, if you start off with some angular momentum, then when you are airborne you cannot. So, what you can do is, what can you change when you are airborne? You can change the distribution around the center of mass. So, the reason you can do somersaults, or you can do flips and do things like that once you are airborne, is because you can still change your moment of inertia. So, when you are airborne you can't change your center of mass, but you can change the moment of inertia about the center of mass, because angular momentum is conserved in that case. A person who is airborne can move segments one another by muscle actuation. This can only affect the moment of inertia about the center of mass. That is why when a diver tucks their body, when they move it, then they start having a greater angular velocity, because they have changed their moment of inertia. Okay. But so, whatever angular momentum they had when they got off the diving board, that is not going to change, that is conserved, because there is no external torque acting on the system once they are airborne. But that they can change, because by changing the moment of inertia they can change their angular velocity.
Flipping is about the center of mass axis, right?
So, I will. So, how do they first gain that angular momentum in the first place? Okay, they have to have some angular momentum. If you just drop a person like that, right, their movement will only be influenced by gravity, no matter how much they move. They have to have some initial angular momentum in order to be able to do that. That is why divers do not just jump straight in. They do some kind of, they use the diving board in a specific way to gain that initial angular momentum. Then with that angular momentum will be conserved when they are in the air, and with that they can play around with how they change their moment of inertia and hence their angular velocity. So, how do you do that? So, for instance, if you wanted to do a backward somersault, for instance, how do you use your So, you have your arms. Okay. What you do is you apply a moment, an internal moment on the arms, to say throw them backward. Okay? You throw the arms backward. What happens now? So, I am applying say a counterclockwise moment on the arms. So, on the rest of the body I am going to have a clockwise moment. Now, I have a support which prevents this from rotating. Now, what does that support do? It generates a reaction force. Now, this reaction force acting about the center of mass of the body causes that rotation, applies the moment. So, that is how you, so if they are on the diving board, depending on how they want to flip, they would move their arms in that manner. So, here if you want to flip backward, so they will stand this way, then move their arms up. Then what happens is the diving board provides that reaction to make them do the back flip. Okay. And once, so this moment that was created, this angular momentum that was gained at the beginning of the flip will remain the same, because there is no other external torque acting on the body, because this is caused by an external torque. The ground reaction force caused the moment about the center of mass, but that cannot change because there is no other, it remains the same because there is nothing else acting on the body once it is airborne other than the force of gravity. Okay. So, that is how they do, this is how you use the reaction forces to perform various movements. Okay. And this is how basically you generate the ground reaction forces. So, if you want to do a backward somersault, your arms if there was no support, the lower body would rotate forward. Since there is a supporting surface, since the supporting surface does not let the feet move, a GRF is created which creates a moment about the center of mass and causes the whole body rotation. So, with this we will kind of wrap up the kinetics portion that we have of this course. So, if you remember so far, initially we did a lot of static analysis. Then in the kinetic analysis we initially started off with modeling as point masses for linear motion, then we looked at angular motion, then using that to find the internal forces. Then we looked at inverse dynamics analysis, which helps you go from segment to segment to find the internal joint forces and moments. And then we looked at some cases of whole body motion, like how do we use this, how how do we use our internal forces against an external support to help make some of these movements. We also looked at the influence of balance. So, this is what we have looked at in kinetics. In the next few classes, we are going to focus more on specifically human walking.